Lab 4 Oscillations by Shannon Schechter. The objective of this lab is to observe and analyze the motion of a spring mass system using tracker software, and then compare and contrast tracker data with model data. In this lab, we will use two principles, Newton's second law and the energy principle. Newton's second law will help us observe the motion of the mass and plot a computational model of the mass in the spring system by predicting new velocities and then resulting new positions. After this is computed, the energy principle will be studied through the graphical analysis at the end. We have that delta E is equal to delta K plus delta U of the spring plus delta U gravitational. For our period, we have that T is equal to 2 pi times the square root of m over K. And for K, our spring stiffness, we get K is equal to 4 pi squared times m over T. Through this equation, we get 6.86 as our spring stiffness. We track the mass on tracker, set the calibration stick and the region where the spring is attached, and then continue to track the mass. Tracker gives us a table that looks like this, and we will take the x and y values that we got from the tracker and then plot them in an Excel file, which will then be used in our coding and will give the actual model the position points. Now we're going to go through our coding. We started over here with the initial conditions, the ball's mass, the position, the velocity, the time, and the initial constant of G and Ks. Now we can see in this part of the coding on Newton's second law. Over here we have the gravitational force that is going to be negative the ball's mass times G in the y direction, the force of the spring that is going to be negative Ks times the compression of the spring times L hat, and F net that is just the sum of these two forces. Then we have the ball's velocity and the formula and the ball's new position formula. They're going to give us the new points in our calculated model using the F net we just found above. L is going to be the stretch of the spring, so it's the ball's position minus the spring's position. L hat is just the direction of the spring force, so it's the L over the magnitude of the L. And S is just the magnitude of L minus L naught, that this is the compression of the spring. This part of the coding, we will have the energy change. We have the kinetic energy as 1/2 times the ball's mass times the magnitude of the ball's velocity squared. Delta K, that is going to be the new kinetic energy minus the initial kinetic energy. And U gravitational, that is going to be the ball's mass times G times the ball's position in the y direction. Delta UG is also going to be the new one minus the initial one. And for U of the spring is going to be 1/2 times Ks times S squared. And also delta US is going to be US, the new one, minus the initial one. Now, as we run this model, we can see the movement of oscillation just as we saw on tracker. And we can see that the black arrow is going to represent the gravitational force, and the blue arrow is going to represent the force of the spring. And for the graph, we chose for this lab the system as the air, the spring, and the mass together. So because there is no outside forces acting on the system, delta E should be equal to 0. In this graph, we have the red line that represents the spring potential energy, the blue line that represents the change in the kinetic energy, the green line that represents the change in gravitational potential energy, and the yellow line that it's the addition of all these energies together, which they equal to 0, and as you can see in this graph. So our energy principle is proven to be true. And for the period in the x position, we got 1.68 seconds, and for the y position, we got it to be 1.55 seconds. These are different because the pad is elliptical and not a circle. So this means the distances are not going to be the same for the x and y axis. The spring is swinging further in the x direction than in the y direction. And because of that, the x-axis distance should be greater than the y-axis distance. Thank you.